Uh, that is Buckingham's Phi theorem. Okay, in a previous lecture, we also talked about Buckingham's Phi theorem, and on that we solved one problem. Okay, actually, that is we have completed in most of the aspects, but still, if you are facing the problem, I think you may face a problem. You have to solve some problem by your own, and then only you can understand it better. So for today's purpose, I just solve one more problem on Buckingham's Phi theorem. Okay, and after that we just move on to the next topic. Okay, so this is how the actually Buckingham's Phi theorem is a procedure. Okay, so you need to just remember the procedure how it is going to solve some formulas and rearrange the formulas. Okay, with the dimensional homogeneity. So that is the use of this Buckingham Phi theorem. Okay, so let me just start it. Yes. So we just see that we have a question like assume the viscous force F that is exerted on a fluid. Okay, this is a viscous force. F that is exerted on a fluid. On a sphere with a diameter d. Okay, d is the diameter. D is diameter. Okay, and having a viscosity that is mu, with the viscosity mu. Okay, and the mass density that is rho. Mass density that is rho, and the velocity of the sphere is v. Okay, velocity of sphere v. Now he says that obtain an expression for the viscous force. So we need to find an expression for this viscous force. Okay, for this viscous force with the help of Buckingham Phi theorem. Now, how to form an expression that we are going to see. So first task is to just form the relationship. Okay. Now, how to form the relationship between dependent and independent variables. So, what is where you know by looking out these terms, you can just say which is dependent variable and which is independent variable. So, we need to find this F, viscous force, which is dependent variable. Okay, which is dependent variable. variable. Okay, which of which is a function of the rest of the terms. So rest of the terms are what? That is the diameter d. Okay, then viscosity mu, then the mass m, then the density rho. Okay, and velocity v. Okay, so these are the independent terms. I just say these are independent, which we have discussed earlier also. These are independent variable or terms. We need to find this. Now, this is actually the relationship between dependent and independent variable, but we need to find the force F. Means actually we just have to get the expression for this force, viscous force F. Okay, means we just find out in terms of formulas. If a simple term, if I ask, that means I just say that just find out in terms the formulas for the F. So the next step, this is our first step. The next step is to dimensions of variables involved. Okay, we just have to write down in dimensional forms. So total number of we just make that in a table like serial number. Okay, then variables, then the symbols. Okay, then dimensions. Okay, so first serial number, that is viscous force. Viscous force. So the symbol is capital F. Okay, and dimension. Now force, how to write that in dimensions? Force is equal to what? Mass into acceleration. So mass and acceleration. How to write acceleration? That is velocity divided by time. So uh, acceleration, that is also the unit of acceleration is meter per second square. Meter is nothing but the length. Per second square is per t square. That means I can write it as -2. Okay. So how the expression has come, we also have talked it earlier. Second is the diameter. Okay. Second is the diameter d. Okay. And in case of a dimension, we just measure in a meter, so that is length L. Then third, that is velocity. Okay, velocity. So velocity we are denoting it by v, and velocity is what? Meter per second. So length per time. Okay. Then next is fourth. Fourth is what? That is viscosity. Viscosity. We are denoting it by mu. Okay, and dimensions for the viscosity, that is m. You have to just solve it for the viscosity. Okay, m l raised to -1 t raised to -1. If you simplify it in Rodman, you can get the answer. Fifth one is the density. Density, we are denoting it by the rho. Okay, and density is equal to mass divided by volume. So mass m divided by volume, that is L cube. means L raised to minus 3. Okay, so we can say that total number of variables here, number of variables. So number of variables are 5. Total number of variables are 5. Okay, and number of fundamental variables, fundamental dimensions are 3. Number of fundamental dimensions are 3. That is what actually this is, M, L, T. So these are 3 fundamental dimensions. Okay. So the number of pi terms, number of dimensional pi terms, number of dimensionless pi terms. Okay, pi terms is equal to n minus m, okay, that is equal to 5 minus 3, that is equal to 2. That means if a pi terms are 2, that is a dimensionless terms, so I just write it is a function of pi 1 comma pi 2, okay, that is equal to 0. If suppose this pi terms is 3, you just have function of pi 1, pi 2, pi 3 equal to 0, like that. Okay, you can modify. Then the next step is to just obtain the equation for pi terms. Obtain equation for pi terms. For pi terms. Okay, so I just say that how to select the pi terms equation. In a previous lecture also, we just have seen that we just have to select the geometrical properties, flow property, and fluid property. 3 types. Okay, means if I just have to write the Buckingham's pi theorem, okay, I just have to use pi1 is equal to this is a geometrical property, that is a T1. Okay, and above that I just write A1. Okay, this is the standard way to write. Next is the velocity property. Above that I just write it as a B1. And the third one is a fluid property, that is a rho. Okay, C1. So these terms are actually a standard term. There is no, I just say, there is no other concept to see that why it has been written. Okay, so we just have to follow the procedure which is given by Buckingham Python. So this is D1 just is a geometrical property, V is flow property, and fluid property. So these 3 properties always are there. Uh, Only pi terms may vary. That is the dimensionless numbers. Pi 2 in the same way D2, okay, raised to K2, then V2 to raised to B2, then rho 2 raised to C2. F is force, okay, which we are going to find, and pi 2 is that is mu, which is a repetitive. If you see, MLT is the repetitive variables, okay, or repetitive dimensions. So that we have to select. that is mu. So this is the way we just have written pi1 and pi2. You just remember the value of here the pi1 and pi2. Okay, for our next procedure, this thing is very important. You just remember this for the understanding purpose. Now next thing is to calculate the value of pi1 and pi2, and before that we just need to find the value of ABC. So pi1 we just have written is equal to d1 raised to a1. Okay, then v1 raised to b1, then rho1 raised to c1. Okay, and f. This thing we have written. Now this is a dimensionless number of the variable. I just write the fundamental terms on the left hand side. Okay, and that is going to be equated with the right hand side. D I just write it as L. Okay, because it is a measure in length. So this is length L raised to A1. Velocity, if I write in the dimensions, that is meter per second. So L raised to t minus 1. Okay, raised to B1. Then density is equal to what we just write mass divided by volume in the dimension terms. We just write it as mass. Okay, volume, that is L cube. So minus 3 raised to C1. Okay, multiplied by F. Sorry. Again, we just have to simplify this F also. So F, I just write it as M L T raised to minus 2. T raised to minus 2. Okay. Now we just find the value of ABC here. M, the value on the right hand side is equal to 0. That is equal to, we just see the value of M on the right hand side, because left hand side the value M raised to power 0, so that we have taken 0. On right hand side, the raised to power, you just have to calculate M raised to first of all search for M and the power ML minus 3 raised to C1. You can see here third term. Okay, so M raised to C1. So we just write C1 here. Then plus 1. Why? Because the next term M raised to power 1 is there. So we just have to write 1. So C1 is equal to minus 1. If you resolve this, you will get C1 equal to minus 1. Then in the same way, L is on the left hand side, you have L raised to power 0, that is equal to, on right hand side, see the power of L, that is A1, plus the next bracket L raised to power B1, so plus B1. Okay, then L raised to minus 3 raised to C1, so minus 3 into C1. Uh, then plus 1. Okay, so this term will keep as it is. Then we just solve for the next is t equal to 0. T equal to 0, you just see the t terms on right hand side, t raised to minus b1. So we just write minus b1, minus 1 into b1. So that is minus b1. And t raised to minus 2. Okay, so the value of b1 you will get here, that is equal to minus 2. If you solve this, you will get the value of minus 2. This is C1. If you put B1 and C1 and calculate for A1 in this equation, you will find the value of A1, that is equal to minus 2. This is the way you just able to calculate ABC. Put the value of ABC in pi 1. Put A1, B1 and C1 in pi 1. So you will get the pi 1 is equal to d raised to minus 2. Okay, multiplied by v1 raised to minus 2 multiplied by density, that is rho raised to power c1, that means minus 1 again, into f. Okay, so if you see here, d1 raised to minus 2, v1 raised to minus 2 and rho raised to minus 1, can I write this as f divided by and rest of the terms in a denominator, like d square, okay, then v square, okay, then rho, okay. So what we have done, we just have taken that inner denominator because the power is minus 2. In a similar way, we just try to solve for pi 2 terms. So if you remember, I have written the pi 2 value. I just again write it down. Pi 2 is equal to d2 raised to a2 multiplied by v2 raised to b2, okay, multiplied by rho 2 raised to c2 multiplied by mu. Okay, so again the same thing, our fundamental dimensions m raised to 0, l raised to 0, t raised to 0, that is equal to, now d in terms of dimensional uh, analysis, I just write l raised to l raised to a2, okay, then velocity, that is meter per second, so l raised to l into t raised to minus 1, that is meter per second, okay, in bracket v2. Then next term, that is rho is the density, mass divided by volume, so mass m, volume is l into l into l, so l raised to minus 3, okay, and whole bracket raised to c2. Then mu, so mu we have written m l raised to minus 1, e raised to minus 1. Okay, so this is the way to write the dimensional, I just say the analysis or the elongation or the expressions. Next step is same, like first of all, we just take the left hand side, m value is 0, that is equal to the right hand side m values, m raised to c2, so we just say c2, okay, plus c2, and m raised to 0, so sorry, m raised to 1, so plus 1, so C2 is equal to minus 1. Okay, so this is the value of C2. Then L again is equal to 0 on left hand side. On the right side, you just see L raised to A2, so plus A2 on the right side. L raised next bracket L raised to B2, so plus B2. Then L raised to minus 3 C2, so minus 3 into C2. Then L raised to minus 1. Okay, so this term will keep as it is. Then T0. Okay, on the left hand side, T raised to power 0 will keep as it is equal to T raised to power minus 1 into B2, so minus B2. Then T raised to power minus 1, so this is minus 1. So you just get the value of B2 that is equal to minus 1. Okay, so if you put B2 and C2 value here, you will get A2 is equal to minus 1 also. Okay, now the same thing which we have done earlier also. If you get the value of phi2, you just have to put the value of A1, A2, B2, C2. Okay, so D raised to power minus 1, then V raised to power minus 1, then rho raised to power minus 1 into mu. Okay, so I just also write it as, if I simplify, mu divided by rho Vd, mu divided by rho Vd. Now what is the next? We have calculated the value of phi1 and phi2. Okay, so if you remember, I have just written as f1 is a function of phi1, okay, and phi2, and that is equal to 0. So I just put the value of phi1 and phi2 here. Phi1 is equal to what? That is f divided by capital F divided by d square into v square into rho. Okay, and mu phi2, the value of phi2, that is mu divided by rho v, that is equal to 0. That is equal to 0. Okay, so one more thing, we can again simplify this as f divided by d square into v square into rho, okay, is equal to f into mu divided by rho Vd. So to calculate the value of capital F is equal to, because we need to find the value of F, the denominator term will take it on the right hand side, so that is rho into v square into d square multiplied by F into mu divided by rho Vd. Okay, so this term actually, you just see here, this term, that is actually the Reynolds number, or we just say this is a pi2 term. Okay, so pi2 is equal to, I just say I can write it as 1 by pi2. Why? Because it's a dimensionless number. Okay, so if I multiply it or divide by any number, that is always a dimensionless number. So that's why I can write anything. If I can divide it by 1 or multiply it by 1 like that. So I can use it according to my convenience. So I know that okay, rho VD is actually a Reynolds number formula. Rho VD divided by mu is Reynolds number. E. We know that. Okay. So here the reverse is that. So we can just reverse it and we can write the our ultimate formula as this is rho V square D square and also it's a function of Reynolds number. So this is how we just have completed our task, that is about the Buckingham's Phi theorem. Okay, so many questions are there. If you practice it at your own level, you can you just have to follow the same procedure for all the problems. Okay, you just get only the different answers. So it's not that much difficult. If you try once or twice, you will get it. Now we just move on to the next topic, that is model and prototype. Model and prototype. Okay, so actually what is model and what is prototype? So model is basically the design, construction and working of the various hydraulic structures or the hydraulic machines cannot be constructed or erected directly for its full use. So actually model is a small scale replica of actual structure. Okay, an actual structure or a machine is called a prototype. So you just remember model is the replica of actual structure. If suppose uh, gravity dam is there, okay, so that is actually an actual structure. Okay, so the actual structure we just say it as prototype. That is actually, this is actual structure. Actual structure. Okay, and if you made a the replica of this gravity dam, okay, gravity dam. If it is an actual structure, that means we are saying it as the prototype. And if you just make the replica, okay, on a smaller scale, we just say it as model. Just see that. So this is the best example for this, how to differentiate model and prototype. Generally, models are much smaller than the corresponding prototype, but in some cases, models may be larger than the prototypes. Okay, so the dam or spillway can be studied on a small scale, whereas working of wristwatch or carburetor can be studied in a larger scale models. Okay, so this is how the model and prototype. You just read out some information about these things. We just see the applications like civil engineering structures such as dams, spillways, weirs, canals, etc. Then flood control and irrigation channels, turbine, pump, compressors, and design of harbors, ship, submarines. This can also be tested with model testing. And then airplane, rockets, missiles. This can also be done with the model testings. Okay, then skyscrapers or high-rise buildings to predict the wind loads and stability characteristics and airflow patterns. So this can be done by the model testing. We just see the next subtopic, that is similitudes. Okay, similitudes. So actually similitude is defined as similarity between model and its prototype in every respect. That is nothing but similarity. It is actually a similarity. The word comes from similarity. Now similarity between what? Between model and prototype. Okay, prototype, between model and prototype. So that is nothing but the similitudes. So the result obtained from the experiments on the models can be applied on the prototype only if complete similarity exists between the model and prototype. So what are these complete similarities? So actually that is, the first is geometric similarities. Okay, geometric similarity. Then second one, that is kinematic similarity. Kinematic similarity. And the third one, that is dynamic similarity. Dynamic similarity. Okay, so we just see one by one these three. First is what? That is geometric. So geometric similarity. So it's a ratio of corresponding length dimension. Geometry is always if you see the term, that is always related with the dimensions. Dimensions in a model and prototypes are equal. If I just draw a diagram, suppose like this. Yes. Just see here. Okay. So this is yes on a smaller. This we are just saying it as, suppose, a prototype. Okay, prototype. If I just make a model of this, I will what I will do. I will just make in a smaller scale like this. Okay, I'll just make it in a smaller scale. So for writing purpose, I just take it as this is width in prototype. Okay, and this is width in model. This is model, nothing but the replica. So this is the width in model. Then length of model. Okay, m. Then height of model m. In the same way, length of a prototype. Okay, and the height of the prototype. So if I have to see the similarity, so the geometric similarity, nothing but the scale ratio for geometric similarity, that is a scale ratio LR. Okay, we are denoting the scale ratio by LR. R. Yes. So I just have to write that, or how to write it. That is LM. L stands for length in model to the ratio of L stands for length in case of a model to the LP in prototype is equal to width in model to the width in prototype is equal to height in a model to the height in a prototype. Okay, that is equal to LR. That is scale ratio. Okay, in the same way, if I just have to write the area scale ratio, area scale ratio. Okay, so area scale ratio, that is equal to AR AM in a model raised to area in prototype, that is equal to, now how to write area, length into width. So length in a model to the width in model divided by length in a prototype to the width in prototype. Okay, that is equal to, if you see this LM by LP and BM by BP, that is LR multiplied by LR. So I can write it as LR square. Okay, so if area ratio is there, you have to write this L square. In the same way, if I just want to write in a volume scale ratio, so can you answer it directly? Yes, volume scale ratio. So we just have to give the answer, that is directly VR is equal to L raised to Q, L R raised to Q. Okay, so this is the way to see the geometrical similarities. Next one is the kinematic similarity. So we just see the next slide, that is kinematic kinematic similarity. Okay, so kinematic similarities are actually, it's a ratio of velocity and acceleration at the corresponding points in a model. At the corresponding points in a prototype are the same. So that is same. We say it as kinematic similarity exists. Okay, so if you just see one example, I will just draw it here. On a larger scale, I can say this as a prototype. Okay, so from here the velocity v, that is the moving velocity v. Okay, so we just have the 2 points. Suppose this is the first point at which certain velocity is there, and this is the second point, again another velocity. Okay, and if you see this hatch portion, that is actually an obstruction, and around that the water is moving. Okay, this example shows like this. So we just say this is a prototype. If I just draw a model, okay, so I just draw a model in a smaller scale, on a smaller scale. Yes, and the same, the water is moving around the hatch portion. Again, I will hatch this. Okay, so this I just say it as model. Yes. and this is how the water is moving around the hatch portion, that is actually an obstruction. Okay, and the same point we have taken, this is our point 1 and this is our point 2. So this is in case of prototype and the model. So if I just have to write the kinematic similarities, that is the scale ratio, I just write the velocity scale ratio, that is VR is equal to V1 in case of a model. Okay, so velocity at point 1 in model to the velocity at point 1 in prototype. So points are same. Okay, you just see points are same. In the same way, velocity at point 2 in a model to the velocity at point 2 in prototype. That is how to write the velocity ratio. In the same way, if I write in acceleration scale ratio, okay, this is acceleration scale ratio. So that is A1. We just have to write A1 in model to the A1 in prototype is equal to A2 in model. A1, A2 is acceleration, different acceleration in case of model to the acceleration in prototype at the same point. Okay, so this is how about the kinematic similarity. Then the last is dynamic similarity. We just complete it in 1 or 2 minutes. The last thing is dynamic similarity. Dynamic similarity. Okay. So dynamic similarity is it's a ratio of all the forces acting in the homogeneous point. So actually, it's an ratio of forces. It's a ratio of forces. Okay, so this we say it as the dynamic similarity. And how to write the force scale ratio? Force scale ratio. So we just have to write force scale ratio. We can able to write it as Fr is equal to some force, suppose that is F1. Okay, in prototype to the some force that is at the same point F1 in model. In the same way, F2 in prototype, okay, divided by F2 in model. Means point is same, okay, but for different cases like prototype or the models. So this is how the, like you see the in case of dams, at the different locations you just have the forces. Okay, force is a vector quantity. It also should have the same magnitude and directions. That is important in case of the dynamic similarities. So that's all for this session. We just stop it here.